Now that we've looked at a couple of examples of linear transformation, let's look at two easy and important facts about them. First fact. Let's let T be a linear transformation from vector space V to vector space W. Then T maps the zero vector of V to the zero vector of W. So I'm putting V and W here because V and W are different spaces. So this might be the zero polynomial and that might be the zero matrix. Or this might be the zero vector in Rm and that might be the zero vector in Rn or something like that. So the zero element in whatever spaces those are. And the reason is, if we take any vector at all in V, then T of 0 times that vector, and here I'm using 0 without a bar to be the scalar real number 0. That has to be equal to 0 times T of V because we can pull scalars out of linear transformations. Now T of V is an element of W, so 0 times an element of W is the 0 element of W. But 0 times an element of V is the 0 vector in V. So here we have it, T of the 0 vector of V has to be equal to the 0 vector of W. So sort of an easy fact. Fact 2 is, again, let's let T be a linear map from V to W. Then instead of defining T on all elements of the vector space V, we could just define it on any basis. Say B equals V1 through Vn of V. Well, for it to be a map, it needs to be defined everywhere on V. So what I'm saying is you don't have to say exactly what it's going to do to every element in V, because if you say what it does to a basis, then that'll tell you what it does to every element in the space V. Sorry about the glare here. So this says instead of defining T on all elements of the vector space V, we could just define it on any basis. So to see this, let's consider some element V in the space where V is not in the basis. Not in the basis B. Well, since B is a basis, then we can write V as some linear combination of basis elements. Let's say C1 V1 through Cn Vn. And by the linearity of T, the fact that it respects linear combinations, we have T of V equals T of C1 V1 plus dot 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 Cn Vn, which is C1 T of V1 plus dot 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 Cn T of Vn. So in order to compute T of V, we really just need to know T of all elements of some basis. It could be any basis at all of the space. So let's do one example of fact 2. So let's say we define T from R3 to R2 by, I'll define it on the natural basis. T of 1, 0, 0 equals 1, 1, 1. Well, actually, this is going to be a map from to R2. So let's define this to be 1, 1. T of 0, 1, 0 equals 2, 3. And T of 0, 0, 1 equals negative 1, negative 1. Well, let's say negative 1, positive 1. So I chose the most natural basis, 1, 0, 0, 0, 1, 0, 0, 0, 1, and define the transformation on that. And then by linearity, we have, say we want to know what is T of 4, negative 2, 3. Well, we can express 4, negative 2, 3 in terms of the natural basis. So it's T of 4 times 1, 0, 0 minus 2 times 0, 1, 0 plus 3 times 0, 0, 1, which is 4 times T of 1, 0, 0, which is 1, 1, minus 2 times T of 0, 1, 0, which is 2, 3, plus 3 times T of 0, 0, 1, which is negative 1, 1. And that is, the first component is going to be 4 minus 3. And the second component is going to be 4 minus 6, it's negative 2 so far, plus 3 is 1. So these definitions of the linear transformation on the basis tell us how to apply the linear transformation to any element at all in the space. For example, to the element 4, negative 2, 3. The end.